Hello and welcome to lecture number 37 of the course Theory of Computation. In the previous lectures, we saw some decidable languages. Then we started seeing the theory of countable sets and uncountable sets. And using that, we were able to see that certain sets are countable and certain sets are not countable. In particular, we saw that the set of all Turing machines is a countable set because it's equivalent to the or a subset of the set of all finitely long strings, whereas the set of all languages is an uncountable set, right? Hence, together this implied that there is a language that is not Turing recognizable, right? Which is also a language that is not decidable, right? Because if a language is decidable, that means it's Turing recognizable as well, right? So, if it is not Turing recognizable, it means it's not decidable as well. But we did not say, or we did not see any specific language that was not Turing recognizable, right? So, we just said that there are languages which were not Turing recognizable. It was an existential sort of proof. It just showed that this is small and this is high in number. The set of Turing machines is small, set of languages high. So, there has to be languages that cannot be captured by Turing machines, right? So, it was an existential proof. In this lecture, we are going to see a specific language which is not decidable, right? So, we will first see that language, and using that we will later be able to see other languages also which are not decidable, right? So, the first language that we will see which is undecidable is ATM, right? It is the acceptance problem of a Turing machine, right? So, given a Turing machine M and a string W, the question is, does M accept W or not, right? So, it seems like a very simple, straightforward question, but this happens to be an undecidable problem, right? So, one natural attempt at trying to show that this is decidable. So, I told you upfront that it is undecidable, but one attempt at trying to show that this is decidable would be to do the following, right? So, let us say U is a proposed decider, right, the U that is mentioned here, and what does U do? U takes M, right, takes the description of M and runs the Turing machine M on W, right, it simulates the running of M on W. If M accepts, U accepts the pair MW. If M rejects W, then U rejects the pair M comma W, right. But so this seems like it has to work. But there is a small issue here. The thing is, if M accepts W, we will accept the pair M comma W, right? Because if M accepts, if M rejects W, we will reject the pair M comma W, right? But there is a third possibility, right? That M may loop on W, right? If U is a decider for ATM, right? If U is a decider, even for the case where M loops on W, U has to reject the pair M comma W, right? So, this is the main issue, right? So, this is only a recognizer. So, a decider must reject M comma W when M loops on W as well. So, a decider must also reject M comma W when M loops on W as well, right? That is not happening here, right? This is not happening here. Not happening here. So, U does not reject M comma W when M loops on W, because you will just continue the simulation. M is running on W and it is looping. So, it just keeps running forever and you will also keep running forever. It will neither accept nor it will reject. So, what we want is something that accepts if M accepts W and rejects when M does not accept W. So, we want it to reject in both cases. when M rejects W as well as M loops on W, and this turns out to be extremely tricky, right? So so again the issue here is that how can the Turing machine, or how can we ever tell whether the machine is looping, right? How can we tell that machine is looping? For all we know, it may be doing some computation over and over again. Maybe it will stop if you let it run for another 100 steps. But how long? So maybe after 100 steps, it's still continuing. So now how long should we wait, right? So when do we know that whether the Turing machine is stuck on an infinite loop, right? If we know that we only have to wait for this much time, then we can wait for this much time. But otherwise, how do we know whether it's going to stuck or get stuck or not? So this seems to be the hardest part, right? So telling whether M will loop on W is not that easy. Or in other words, we are asking, so what is the opposite of getting stuck on a loop? The opposite of getting stuck on a loop is like being decisive and stopping or halting. So the opposite is, can we know for sure that M halts on W? If we know M halts on W, you can run it. We know that it is going to halt, which means it's going to accept or reject. But if we know that it is not going to halt, even then we know that the only way it is not going to halt is if it is looping. Right? Then also we can reject. Right. So in a sense, the real challenge is in actually telling whether, or determining whether M halts on W or not. So this is the real challenge. Okay, so if we can tell whether M halts on W, then we just figure out whether M halts on W. If it halts, then we just run the Turing machine that we described above, U, right, this one, right. It runs M on W, and we know M halts on W. So either M accepts or rejects, one of these cases will happen. Again, if you know that M does not halt on W, even then we know that M does not halt on W, then you can immediately reject, because the only way it does not halt is M loops on W, right. So the challenge or the difficulty is captured by this language here, which I am calling it as HALT-TM. So given a Turing machine M and a string W, HALT-TM is asking whether does M halt on W. So given a Turing machine M and a string W, does M halt on W? So this is called the halting problem. For our class, we will also call ATM as the halting problem. And because if we can solve HALT-TM, we can also solve ATM, right? In the manner that I just said. You decide HALT-TM, and if M does not halt on W, then you immediately reject the ATM instance, because it's not going to get accepted. If we know M halts on W, then we can just run M on W and let it halt either way, accept or reject, right? So this is the real halting problem, is HALT-TM, deciding whether M halts on W. But sometimes we may also refer to the ATM, the language ATM, as the halting problem. Okay. Right. So hopefully it is clear that the difficulty in deciding whether M accepts W lies in determining whether M loops on W or not, or in other words, M halts on W or not, right? So that is the challenge there, and that's why it's called the halting problem, and this is also undecidable, right? So what we are going to see now is the proof that ATM is undecidable, right? And yeah. So we will prove it by contradiction, right? So think about it. We want to show that whatever algorithm that we can try, none of these algorithms work. Meaning, there is no algorithm that can decide this problem, right? So how do we rule out all possible algorithms? So that's the interesting thing about this proof, right? So in fact, we will use a proof that is similar to the diagonalization proof in some sense. So when you see it, you will realize where the diagonalization happens. Right. So we'll assume that ATM is decidable and derive a contradiction, right? So if it is decidable, means there is a decider for ATM, right? So let H be the decider, okay? So which means it takes a pair MW as input, right? And H accepts the pair MW if M accepts W, and rejects the pair MW if M does not accept W, right? So this has two parts, right? One is that M rejects W, and two is M loops on W. So in either case, we want H to reject the pair M comma W. If M rejects W as well as M loops on W. So H is a decider, which means that H never halts. H never loops. H is always going to halt, right? So we will derive a contradiction, right? So let's see how we get the contradiction, right? So the theorem is that ATM is undecidable. So what we do is we assume that ATM is decidable, and which means you can assume that there is a decider H, like we said. Now using that H, we are going to build a machine D. Okay, we are going to build a machine D. So what does D do? Okay, so D takes some description of a Turing machine as input, right? So D takes as input like the description of a Turing machine M. Okay, that's what I have written here on input M, right? So what it does is it represents D actually runs H, where H is the decider for ATM, right? And D, but then the input of H is of the form a machine and a string, right? D gets as input a description of a machine. So what does H get as input? H is given input. So the machine M is the input M, and the string W is also the description of M, right? So we have seen that every Turing machine has a description, right? You can encode the description of a Turing machine. So what D does is it takes M which is the input given to it. So which is the M which is the input for H, but H also needs a string as input. So the string is going to be the description of the Turing machine M, right? So you have M which is the Turing machine, and the description of the Turing machine is a string that is going to be fed to M. So we run H on the Turing machine M, and the description of the Turing machine is a string, right? So the same Turing machine M appears in two ways. One is the input string, and one is the Turing machine, and two is the input of the Turing machine. So what does D do? D runs H, which is the decider for ATM, on the pair M and the description of M. And then it does one more tricky thing. So H is a decider, which means we know for sure that H will accept or reject, right? So if M accepts the description of itself, H will accept. If M does not accept its own description, right, H will reject. Meaning if M rejects its own description, H will reject. If M loops on its own description, even then H will reject, right? So in either case, H will reject. Now what we are going to do is, what does D do? D actually flips the output, right? So flips the output of H. So if H accepts, D rejects, and if H rejects, D accepts, and we know for sure that H will halt, right? So what does D do? D runs H on the input M and its own description as a string, and if H accepts, D rejects. If H rejects, D accepts, right? So just to give an like pictorial description, right? D is given M as input. So inside D, it runs the Turing machine H, which is the decider for ATM, with the Turing machine M and its own description as the input string, right? So then H says accept or reject, and what does D do? D flips whatever H is saying and outputs. So this is the output of D. It just flips the output of H. So this is what it does. So far so good. So all that we have told so far is, if ATM is decidable, there is a Turing machine H which is a decider for ATM, right? And if H is a decider for ATM, using H as a building block, we are making another machine D. What does D do? D takes a description of a Turing machine as input, feeds H the same Turing machine and its own description as input, and whatever H does, it flips the output, right? So far it's fine, there is no contradiction so far. So let us denote by this symbol, this notation, D and parenthesis the description of M. This stands for what does D do when it is fed M as input. What does D do when it is fed M as input, the description of M as input. So let's see, what does D do? What does D do? It takes the output of H and flips the output, right? And H is a decider for ATM. So H will accept if M accepts its own description, right? So DM will reject if M accepts its own description, and DM will accept if M does not accept its own description, right? So does not accept again means two possibilities. One is reject and two is loop. So D of M is what does D do on M. It is accept if M does not accept its own description as input, and reject if M accepts its own description as input, right? So DM is accept if M does not accept its own description, and reject if M accepts its own description, right? Again, so far so fine, so good. Now where do we get the contradiction? The contradiction comes when D is given its own description as input. Okay, so in place of M here, right? So in place of M here, we give D. So what does D do when its own description is given as input? So it's very simple to do, very simple to see. So wherever we see M here, we just replace M with D, right? That's all that we have to do. So let's try doing that. So in fact, I have already done that. I copy pasted everything that I said here, but wherever M was there, right, this five places, I have replaced it with D. Okay, so that's also straightforward, right? M can be any Turing machine, we replace it with D. But when you read this now, there is a interesting thing that is going on. So what is the left hand side? Left hand side is what does D do when given its own description as input. This is what this means, right? What does D do when given its own description as input? And what do we have here? It accepts if D does not accept D, and rejects D if D accepts D. So this is a very strange thing. So we are saying that D accepts its own description. D accepts D if D does not accept D, and D rejects D if D accepts D. So this does not make sense. What we are saying is that whatever D does on its own description as input, D is supposed to do the opposite of that, right? So suppose D does not accept D, then D is supposed to accept D. Suppose D accepts D, then D is supposed to reject D. So it doesn't make sense, right? So that's the contradiction. So what we want here, what is going on here is whatever D does on its own description as input, D has to do the opposite of that. So this just does not make sense. So whatever D does on its own description as input, it has to do its own opposite. That is the contradiction, right? So maybe I'll just highlight this part. Whatever D does on its own description as input, D is supposed to do the opposite of that. And that is kind of an absurd statement. D does something on something when it's given its own description as input, but then we are saying that D should do the opposite. But then we will again say that it should do the opposite of whatever it's doing right now. So that's the contradiction, right? So let me just recap, because it's such an important proof. H is a decider for ATM, right? H is a decider for ATM. And what does D do? When given M as input, it feeds H with M and its own description as input, and it flips the output of H. So what does D do when given M as input? It feeds M and its own description to H. If M accepts its own description, then D rejects it. If M does not accept its own description, then D accepts it. So D accepts M if M does not accept its own description. D rejects M if M accepts its own description. It's fine so far till we decide to replace M with D. So then D accepts its own description if D does not accept its own description, and D rejects its own description if D accepts its own description. This is the contradiction. So this is saying that D should do the opposite of whatever it's doing right now. But when it does the opposite, we'll say, no, this is also not correct because it should do the opposite of whatever it's doing right now. Right? So that's the contradiction. Right? So this means whatever it does, it should do the opposite, and which means it's an inconsistent situation. So maybe this may seem confusing. So I suggest that maybe think over it a day or something. But I'm also going to give another viewpoint for the same thing. So if you remember, we saw the explanation that real numbers are uncountable. So we listed down, we assumed that real numbers are countable. We made a listing, and then by flipping the entries in the diagonal, we identified a real number, which was not captured in any of this listing. And that's the contradiction. So we can see this proof that HALT-TM is decidable, right? So we can see this proof as a diagonalization proof. So notice that the contradiction, so at the end we got the contradiction, and the assumption that we are contradicting is the assumption that HALT-TM is decidable, right? So let us see another perspective for the same proof, right? Suppose HALT-TM was decidable, right? We can build a table, right? So we have already seen that the set of all Turing machines is countable, right? So now let us build the following table. So the columns are descriptions of Turing machines, and the rows are indexed by Turing machines, right? So we have to see the rows, the indices of the rows as Turing machines, right? M1, M2 as Turing machines, and the indices for the columns as inputs. So the inputs here are also descriptions of the Turing machines, but they can also be viewed as strings, right? So let's see how to fill this. So what does M1 do when it is fed its own description, right? So let's say it accepts. What does M1 do when it is fed the description of M2? Let's say it rejects. What does M1 do when it is fed M3's description? Let's say it accepts. What does M1 do when it is fed M4's description, right? So M1, M2 are all the Turing machines. So as I already said, the set of all Turing machines is countable, and we can list them, right? So perhaps M1 loops on the description of M4. So we say loop. Similarly, what does M2 do when it is fed M1, M2 do with it's fed M2, and so on. So we can fill this table with accept, reject, loop, whatever, right? So that's how we have filled it. So reject and loop I have written in red color, accept in black color, right? So what does H is the decider for HALT-TM, right? So what does H do when, okay, there is some issue here, is given as input. What does H do when Mi and the description of Mj is given as input, right? So when Mi and the description of Mj is given as input, so H will accept if Mi accepts Mj, H will reject if Mi rejects Mj, H will also reject if Mi loops on Mj. So it's the same table as we have here, right? So what does H do when M1 it is fed M1, it will accept, right? What does H do when it is fed M1, M2's description? It will reject, right? What does H do when it is fed M1, M4's description? So here it is loop. but then that means it's not accepting, right? M1 does not accept the description of M4, so H will reject. So this table here is what does H do when it is fed Mi and the description of Mj. So the rows indicate Mi and the columns indicate the description of which Turing machine, right? So it's the same table as before, just that whenever M1 or whenever Mi loops on Mj, we say H rejects that Mi comma Mj, right? Because H does not loop, H is a decider. So Mi loops on Mj means Mi does not accept Mj, so H rejects Mi comma Mj, right? So it's the same table. If you see accept, reject, accept, loop, now it is accept, the first row accept, reject, accept, reject. Second row is accept, accept, reject, loop. Over here we have accept, accept, reject, reject. So loop is replaced by rejects, right? So and we know that by assumption ATM is decidable, so H is there, right? Okay, so far it's just standard things. Now where does the issue arise? So the issue arises when you realize that H is a decider, right? H exists, a decider for ATM exists, and if H exists, right, by the construction that we have seen over here, if H exists, I can make D from H, like by building this thing around it, right? So D is just a Turing machine that is using H as a subroutine, right? If H exists, D also surely exists, right? So which means ATM is decidable means H exists. Since H exists, D also exists, which means D is a Turing machine, which is a decider, which means in the listing of all the Turing machines M1, M2, M3, M4, some point D appears, right? So maybe it is M100, maybe it is M523, right? We don't know. So the point is that in this listing D appears at some point, right? Right? So it appears in the row, it will also appear in the column at the corresponding point, right? So now how did we make D, right? So we wanted D to do the opposite of whatever each Mi does on its own description, right? That's what we said here. What does D do on M? D accepts M if M does not accept its M, and D rejects M if M accepts M. So we wanted D to do on each Mi the opposite of what Mi itself does on its own description, right? So what does D do on M1? The opposite of whatever M1 does on M1. So M1 accepts M1, so D rejects M1. M2 accepts M2, so D rejects M2. M3 accepts M3, so D rejects M3. M4 rejects M4, so D accepts M4. So it's all clear, right? So D, basically what is D doing now? D is kind of picking the diagonal entries here, and D is flipping the diagonal entries, right? Again, this is all very clear, right? So because D is supposed to do the opposite of whatever, so D, what is D supposed to do on M? The opposite of what M is supposed to do on M, right? So basically D is supposed to be flipping this diagonal, which is what we have here. Again, so far it's fine, till you realize that D also appears as a column, right? So now the dth row and the dth column, when you coincide, now what happens? This is the interesting thing, right? Because suppose this cell where dth row and dth column was to be accept, but then D is supposed to flip the diagonal entry. So the diagonal entry says accept, then D is supposed to flip it, so it should be reject. But then if it says reject, then D is supposed to flip it again, it should be accept. So there is nothing that we can fill here in a consistent manner, right? Because D by definition is supposed to flip the diagonal entry, but then this itself is a diagonal entry, so how it cannot flip, right? So that is a contradiction. So now you see the parallel between the diagonalization that showed that real numbers are uncountable and this, because there also in the case of real numbers, basically we looked at number 0, 1, 2, 3 something, right? That's a 3.012, 2.6362, 5.243, some numbers, and then we picked a number, let's say, which is which is different from 0, 6, 3. So we picked a number 0.174 something, which differs from the first number in the first decimal place, second number in the second decimal place, and so on. Similarly, D is designed to be different from M1, M2, M3 and so on, but then D is now also has to be, as a consequence, it also has to be different from itself. That's a contradiction. So which means D cannot be featured in this listing. But then by assumption, we assume that there is a decider. Right? So that's the assumption that is wrong. Right? This cell over here, we don't know what goes here. So that's a contradiction. Right? So maybe I'll just summarize this proof once again, because it's an important proof. I don't think I think it's worth repeating. Right. So why is this diagonalization? So suppose ATM is decidable, which means there is a decider for ATM. So now let us see, we can enumerate all the Turing machines, M1, M2, M3 and so on. We can build a table of what each MI does on when fed the description of MJ. Right. So this could be accept, reject or loop. Now what does H do on when given MI and the description of MJ as input? What does H do when given this as input? It will be the same table, except that H is decisive. H will never loop. So H will reject when MI loops on MJ. So it's the same table, but with all loops replaced by rejects. Right. Now by definition of D is supposed to flip what M does on its own input, its own description as input. So D is supposed to do to M the opposite of what M is supposed to do to M. Right. D is supposed to do to M the opposite of what M is supposed to do to M. So D is supposed to reject M1 since M1 accepts M1. D is supposed to reject M2 because M2 accepts M2. D is supposed to reject M3 because M3 accepts M3. D is supposed to accept M4 because M4 rejects M4. Right. The issue arises when we start worrying about what should D do on its own description. So D is supposed to look at the diagonal entry and flip the entry, but then D itself contains a diagonal entry. So there is nothing you can fill in there in a consistent manner without a contradiction. So that's the issue. Right. So again, this is the diagonalization based proof. It may be, it is not that difficult, but it may be a bit tricky. So think about it for a day or two. I think it will become clear, right? So that's the proof that ATM is decidable, right? And in fact, as I said, HALT-TM is also ATM is undecidable. In fact, that also means that HALT-TM is undecidable. Which we can prove, but we will not do it now. And I think we are probably at the end of today this lecture. In this lecture number 37, where we just saw the proof that ATM is undecidable. Right? So there are some more small things that I want to say, which I will cover in lecture 38. Thank you.